Okay, so hi, welcome to this next video in linear programming. So in the previous video, we gave a characterization of extreme points in terms of the associated matrix of tight constraints. And in this video, we're going to use that characterization in order to demonstrate this important relationship between extreme points and basic feasible solutions. In fact, what we're going to show in this video is that extreme points and basic feasible solutions are the same thing. Extreme points are just the geometric representation of basic feasible solutions. So that's the idea for this video. So the correspondence, slightly more formally, is that if you give me a linear program in standard equality form, so that's like this, where we're maximizing some linear objective function subject to matrix equality constraints and variable non-negativity constraints. A standard assumption for standard equality form is that our rows of this matrix are linearly independent, so that's what we're also assuming that. And also, by the way, we're just using M instead of A. Usually we would call this AX equals B for the notation for the matrix equality, but we're going to reserve a notation A and B for something else, so we're just using different letters here. So M and F are the matrix and the vector here for the standard equality form. So if that is our standard equality form linear program, and then we take P to be the polyhedron of the feasible points, so the points that satisfy all those constraints, and then we take a particular point x bar in the polyhedron, so it's a feasible solution for our linear program. Then what we have, the conclusion, is that x bar is an extreme point of the polyhedron if and only if x bar is a basic feasible solution. So in other words, that's saying that extreme points equal basic feasible solutions. They are the same thing. So that's what we're going to show in this video, that correspondence. Okay, and so there's two directions to show there. It's an if and only if. So let's just show both those directions. So first of all, if we're starting with a basic feasible solution, let's start with that assumption, and then we'll show that that point is an extreme point. Here's our linear program in standard equality form with the assumptions that we had above. Without loss of generality, we can assume that it's in canonical form for some basis B, subset of n, which is, again, little n brackets that's indexing. That's all the column indices, that's all the columns. So we can assume it's in canonical form for any basis. So if we are starting with a basic feasible solution, then it must be a basic feasible solution for some basis. So let's assume that we're in canonical form for the basis, that our basic feasible solution is the corresponding basis for that. So I hope that makes sense. So we're starting with a basic feasible solution. Well, what is the basis that is associated to that basic feasible solution? Let's put the linear program in canonical form for that basis. Then we're going to show that that point is extreme. It's an extreme point. So the polyhedron is given by all the constraints in standard equality form, but we're typically more used to seeing those constraints as being written as intersections of half spaces. In other words, that it's a system of less than or equal to constraints, because that was the format that we had in the previous video, and that was the format that we needed in order to use that the characterization of the rank of the matrix of tight constraints. So first of all, let's just reformat things so that the polyhedron is more clearly of that format. So how do you go from a standard equality form to going to all less than or equal to constraints? So we've done this type of thing before. It's not that difficult. You just, if mx equals f, then you know that mx is less than or equal to f and is greater than or equal to f simultaneously. So you impose double the constraints here, where we have mx is less than or equal to f, and instead of saying mx greater than or equal to f, you just multiply by -1 on both sides to turn the greater than or equal to into a less than or equal to. So you have minus m times x is less than or equal to minus f. And so those two sets of constraints are equivalent to the original system of equality constraints. And then finally, for the variable non-negativity, well, this is a greater than or equal to constraint. So just multiply by -1 basically, and you just so it's negative identity matrix times x is less than or equal to 0. And that's equivalent with saying x is greater than or equal to 0. So that system is equivalent to the original system, and now we're of the right format. So let's call this big block matrix A, and the block vector, we'll call that B. And so that'll be the A and the B that we're referring to in this proof. Okay, and so we have three types of constraints. Constraints from the first block, second block, and third block. And so I've just labeled them 1, 2, and 3 for each type of constraint. And then all of them together are equivalent to the original constraints. So, okay, so we're assuming that x bar is a basic feasible solution. So if it's a basic feasible solution for this basis B, then what we know is that it satisfies the constraints. So it satisfies mx bar equals f and x bar is non-negative. And since it's basic, we know that the non-basic components of x bar are all zeros. So what does that tell us about the tight constraints of this system right here that we've been given? Because again, we are using the characterization from the other video, so we need to figure out what the matrix of tight constraints is first. So the tight constraints, well, it's going to be the first block and the second block. Those will be part of the tight constraints because mx bar less than or equal to f. Well, that's true because we know that mx bar, so that's tight, I mean, because mx bar is equal to f. That's what we're starting with by assumption. And then same thing for the second block of constraints. Those less than or equal to are also tight for the same reason. It's the same thing here because mx bar equals f. And then finally, for the type 3 constraints coming from this third block, a constraint there is going to be tight if and only if the associated component of x is equal to 0. And so we don't know all of the components that are zeros, but we do know that the non-basic components are definitely all zeros. So let's pick out just the non-basic components. So that of type 3, it's this sub-block of type 3 here, which is the negative identity matrix, which is capital N by capital N. So this is just the submatrix of the identity matrix being picked out by the non-basic indices, and so this is still square because it's non-basic rows and non-basic columns, but that's not wide enough. So we just have to pad with zeros. That's what this 0 is. It's a 0 matrix, which is a bunch of columns of zeros, which is padding this so that the number of rows here matches the number of rows of m. Sorry, I'm sorry, the width of a row, which is the same thing as the number of columns, matches the number of columns of m and of minus m, so that it fits in this. So these zeros do appear in this negative identity matrix here, but of type 3. But the thing here is that this identity matrix was the same size in terms of the width as the width of m and minus m, whereas this is a square submatrix, so it's not the same size. So these zeros, we're just explicitly writing them out now, whereas they're just implicit as part of the identity matrix here. But anyways, the point is that this type 3 sub-block is picking out exactly the components that of x that are the non-basic components, and those are going to so everything's less than or equal to 0. Corresponding to the fact that all of the x bar components are greater than or equal to 0, but in particular we know that the non-basic components, which are picked out here, are exactly equal to 0 because it's a basic solution. So this part of type 3 also holds tight. So A equality, the matrix of tight constraints, it consists of the first block, the second block, and that part of the third block that we just talked about. So of type 1 and 2, we have all the constraints, and of type 3, we have some of the constraints. By some, we mean specifically the non-basic constraints. And then I put this blue plus here just to indicate that we could have more constraints as well coming from type 3. We have all of type 1 and type 2 already, but some of type 3 might be missing. So they could also be here. There could be more, but we just don't know. The only ones that are guaranteed to be here are the non-basic components, because those are the ones that are definitely zeros since it's a basic solution. So the part in black is the only part that's guaranteed to be there. So A equality is that then. The black part is the guaranteed part of A equality. So what's the rank of that matrix? Again, there could be more rows, but if we can show that with just this part, which could be all there is, if that has full column rank, then that's enough, because if you add even more rows, that's not going to change the rank anymore, since it's already full column rank. So what is the rank? We're claiming that it is indeed n. The rank of A equality is n, and that will suffice to show that x bar is an extreme point. That's equivalent with showing that x bar is an extreme point. So how do you prove that the rank of this matrix A equality here is n, which is the number of columns? Well, the proof is that you find n linearly independent rows of the matrix. And the way that you do that is first you note that the linear program is in canonical form for this basis B. So the submatrix of M, picked out by the B columns, is an identity matrix. That's part of what it means to be in canonical form for a basis. So let's just look at the type 1 block and the type 3 block, the part of type 3 that appears, I guess, is what I mean here. And for those, so let's just split everything up into the non-basic and basic parts. So we've already done that for the part down below in the second row block. For the top row block, we have the non-basic components of M, and then the basic columns of M. And the basic columns of M are identity matrix columns, because we're in canonical form there. So what we have is that we can look at our matrix. This type 1 and type 3, this is just a submatrix of A equality, which is itself a submatrix of the overall matrix A. But anyways, this is just part of A equality. And actually, the claim here is that here we have n linearly independent rows just amongst this part. And that's because you can see that we have an identity matrix here and an identity matrix, well, the negative of an identity matrix here, and zeros here in this this block, and all that together. Then it doesn't matter what this M part is, but all that together will show you that all those rows are linearly independent because of where the ones and minus ones appear, and then the zeros, down here appear. So that suffices to show that all the rows are linearly independent. If you want an even more straightforward way, to see that all the rows are linearly independent, well, you can compute the determinant of this, and it's a square matrix, so the determinant can be computed, and it's non-zero, because what you can do is you can just reshuffle the rows and columns around so that this block, this identity block matrix, shows up as the left block, and this minus identity matrix shows up as the right block here, and then this zero block is here in the bottom left, and then the M is you just flip each of the row blocks, and then what you have is an upper triangular matrix, and then for an upper triangular matrix, the determinant is the product of the diagonal entries, and the diagonal entries are plus and minus ones. So then the overall determinant is plus or minus 1, and the determinant doesn't change when you reshuffle rows and columns, except for possibly changing sign. That's the only thing that can change. But if it's non-zero, then just flipping the sign doesn't change the fact that it's still non-zero. So anyways, so you have a non-zero determinant, so everything's invertible. So the rows in particular are linearly independent. So that's another way you can see that. Anyways, all that is to say that all these rows right here are in fact linearly independent, and we have little n of them, because in the top block you can see that we have the number of rows in that top block is cardinality of B many rows, and then for the bottom block it's cardinality of n many rows, and B and capital N form a partition of all the columns, which is little n. So cardinality of B plus cardinality of n is little n. And so that's how many rows there are, and they're all linearly independent. So what we've just done is we've found n linearly independent rows. And so that means that so these rows all appeared as part of A equality, and so we've just found n linearly independent rows inside A equality. And so then that means the rank of A equality is equal to n, because it couldn't be anything larger since there's only n columns. So that was at most what it was, but in fact we've explicitly found that the rank is n by showing these linearly independent rows. So yeah, so the rank of A equality is n, and that, as we've already shown, is equivalent with showing that x bar is an extreme point. And so there you go. What we've just done is we've just shown that that x bar is a basic. If it's a basic feasible solution, then it's also an extreme point of the polyhedron. Okay, and then what about the converse? Is that true as well? Well, yeah. I mean, of course it is. It's just how do you show that? So what you do is now you're supposing that x bar is an extreme point, and you want to show that it's a basic feasible solution for some basis. So we're gonna construct a basis for which it's a basic feasible solution. So it's an extreme point. So in particular, it's in the polyhedron. So that means that it satisfies all of the constraints. So the matrix equality constraints and variable non-negativity constraints. And so what you do is you pick out the base. You pick out the indices for which x bar is strictly positive. So x bar, it's going to consist of components that are either zeros or they're strictly positive because everything is greater than or equal to 0. One of the two. So look at the indices for the components that are strictly positive, and then what happens is that m times x bar. Well, first of all, you can just split it up into the j components and the not j components, and for the not j components. By definition of what j is, that's the ones where x bar is positive. So then for the not j components, then x bar is 0. So the not j components are all 0. So this part just vanishes, and you're just left with mj times x bar j, and that equals f because we're assuming that m times x bar equals f, and we started with that. So okay, so we've just taken a linear combination of the columns of m sub j, and we've gotten f. And now the question is, are those columns of m indexed by j, are they linearly independent? Because if they are, then what happens is that you can extend those linearly independent columns to a basis for the linear program, and then x bar will be a basic feasible solution for that basis. And it doesn't matter; you just extend to any basis. Starting from j to extending to any basis, and x bar will be a basic feasible solution for that basis. So anyway, so the question just becomes, are the columns linearly independent? And so the claim is, yes, they are. They are linearly independent. So why is that true? Why are those columns linearly independent? Well, the reason is that because if they weren't, then what you'd have is some vector d hat with cardinality of j components. It's some non-zero vector with cardinality of j components, such that when you did m sub j times d hat, you get 0. So you'd have something in the null space of some non-trivial vector in the null space of m sub j. So there's some linear dependence amongst the columns is what we're assuming, because we're trying to contradict ourselves to show that the columns actually are linearly independent. So if there's a linear dependence, you have something in the null space of m sub j, and so then that means that there's some vector d in Rn, some non-zero vector in Rn that's in the null space of the overall matrix M, and that's just because you started with this vector d hat, and now you just pad d hat with zeros, because d hat, the only components that existed for d hat were the components indexed coming from indices of j, because you had a component for every column of m sub j. So for every component of j, there was a index of j. There was a component of d hat. But now you just fill that up to be a vector in Rn corresponding to taking a linear combination of the overall matrix M. So you just do that by just putting zeros for all the other components that weren't indexed by j. So d indexed by j is that original vector d hat that we had from linear dependence, and then for the not j components, this vector d will be all zeros. You're padding with zeros there, and so that's in the null space of M, and because of that, because you have this vector in the null space of M, what the idea is then, the contradiction is that x bar is actually not an extreme point, because what you can do is you can perturb x bar in this null space direction. This is very reminiscent of the proof from the prior video. We did a perturbation in a null space direction once we assumed by contradiction that we had a null space direction in the first place. So we're doing a similar thing here. So you take x bar, which is the point we're claiming is an extreme point, and now perturb it. And you take x bar minus epsilon d and x bar plus epsilon d. So epsilon is some small positive constant, and then d is that vector d in the null space of M. And of course, x bar is between those 2 points, but now the question is, are those 2 points in the polyhedron, in P? And the answer that we're going to show is yes, and that will contradict the fact that x bar is supposed to be extreme. So what does it mean for these points, x bar plus and minus d? So those are the perturbation points. What does it mean to be in the polyhedron? It just means that they satisfy the constraints, so the matrix equality constraints and the variable non-negativity constraints. So matrix equality constraints, those are immediate because m times x bar plus or minus epsilon d, we have 2 points, one for the plus and one for the minus. You just distribute the m in, and then d is in the null space of m. So this part just goes away, and you're just left with m times x bar, and we already know that that equals f because x bar is a feasible point. So then you get m times these 2 points also equal f, and so they both satisfy the matrix equality constraints. And how about for the variable non-negativity constraints? Well, break it up into the not j components and the j components. Again, remember, j is the components, it's the indices for which the components of x bar are strictly positive. So we're going to use that definition. So those 2 cases, so for the not j components, what you do, well, they're non-negative because x bar for those components plus epsilon d for those components, well, d for the not j components, those are all zeros, because remember we started with d hat, we started with this d hat vector, and then we padded with zeros for everywhere else. So d hat, those indices were the j indices, indexed by capital J here, and then everything else was zeros. So for the not j components, they're all zeros. So epsilon times the 0, this is just the 0 vector. That epsilon times the 0 vector is also 0. So this part just goes away then, and you're just left with x bar for the n not j components, and we already know those components are non-negative because we know that all the components of x bar are non-negative. So in particular, the not j components are. So that shows that for these perturbed points, that for these components, they're non-negative. Now, how about for the j components? For the j components, so that's case B here, we know that so it's x bar sub j plus or minus epsilon d sub j. For x bar sub j, those components are strictly positive. That's by definition of what j is. And these are the strictly positive components of x bar. And so now the idea is, again, very reminiscent of the proof in the prior video. Since these components are strictly positive, then we have slack here, because all we need is for these components overall, once you plus or minus epsilon times d, for those components, you need all of them to be non-negative. So this is strictly positive here, and so you have a little bit left over. So first of all, if d for these components is if this overall quantity, if you're adding a positive amount on, then this is positive plus a positive amount. Of course, that's positive, and it's still non-negative then, so that's fine. The worry is that what if you're subtracting something, which is definitely going to, you're doing plus and minus. You have to account for when the sign is positive and when the sign is negative. So if you're subtracting something, then the worry is that the thing you're subtracting is very large, or too large at least, and that'll take this. It'll overwhelm this positive part, and the positive plus a very negative thing will become negative, and then it'll ruin feasibility. It won't be non-negative anymore. But you can account for that because you're just going in the direction of d. You're not actually it's not actually the vector d, you're just going in that direction, but you're scaling by epsilon. So you just scale epsilon down small enough so that all those components, when you subtract off, those components, they're just, they're very, very small. And they're small enough so that they don't overwhelm the slack that you have here. So I have something positive here, and I might be subtracting something here, but it'll be so small that the overall thing will still be non-negative, because we're just going to choose epsilon. You just do what this blue comment says. You just choose epsilon small enough so that these j components are still non-negative when you do x bar plus or minus epsilon dj. Okay, so again, you're, so there's multiple components of j that you're going to have to pick an epsilon that satisfies the constraint, and then you just choose the smallest epsilon amongst all those constraints, because that'll work for all of the constraints, and that epsilon overall will work, and then that'll show that x bar plus or minus epsilon times d is non-negative, because we've shown it for both the not j components and the j components. That's all the components then. So we've just shown that x bar plus and minus epsilon d it satisfies the matrix equality constraints and the variable non-negativity constraints, so these points are both in the polyhedron. But the contradiction that we now get is that x bar is strictly between those 2 points. It's half of x bar plus epsilon d and plus half x bar minus epsilon d. So x bar is strictly contained in the polyhedron because it's strictly between these points, x bar plus epsilon d and x bar minus epsilon d. And so that implies that x bar is not extreme. And that is a contradiction with what we originally assumed, that it was an extreme point. And so therefore, the columns of m sub j must be linearly independent, because that's what that was the thing that made this all go wrong. When we assumed that m sub j, those columns were linearly dependent, we got this null space vector for the overall matrix M, and then we could perturb points in the direction of that null direction, and that's what contradicted the fact that x bar was supposed to be extreme. So actually, that null direction couldn't have existed in the first place. So so then the columns of m sub j must actually be linearly independent. Okay, so j indexes linearly independent columns, and so since those vectors are linearly independent, you can extend these linearly independent columns of j to any basis, b, which contains j. And then no matter which basis you picked that you extended to, there's at least one. There could be multiple, though, but there's at least one. So for whatever basis you've extended to, x bar is a basic feasible solution for that basis. I shouldn't say a basic feasible solution, actually. I should actually say the basic feasible solution for that basis, since we know it's unique. But anyways, it doesn't matter right now. All we wanted to show is that x bar was indeed a basic feasible solution. Because what we just did is we went from an extreme point, and we started by assuming that x bar was an extreme point, and we just showed that now it's a basic feasible solution. And so those are the two directions of the proof, and we can finally conclude that x bar is an extreme point if and only if x bar is a basic feasible solution. And so that is going to give us some pretty deep geometric insight into what is happening with the simplex algorithm, and we'll elaborate on the consequences of this result in the next video. So that's it for this video. Thanks for watching.